Hello everyone, welcome to next lecture in the topic of spectral reflectance curve of few commonly occurring earth surface features. Till last lecture we discussed in detail about the spectral reflectance curve of vegetation, the factors that influences it, redage, and also what other factors may influence the final reflectance that we obtain from a remote sensing sensor. In this lecture we are going to start with the spectral reflectance curve of soil, which is another one of the most abundantly occurring feature on the earth surface. So, the spectral reflectance of soil is a very simple curve. It is not like as complex, or it will not have any kind of like complex dips and peaks as that of vegetation. An example is given in this particular slide. So, if you look here, in general the reflectance curve of vegetation may not have lot of this peaks and valleys that we observed in the reflectance curve of vegetation. These characteristic features will be absent. Also one more thing we may notice, the reflectance in general linearly increases with increase in wavelength. That is, as the wavelength increases, the reflectance in general increases. There may be some ups and downs, but not as sharp as vegetation, and also like not like very high dips may not be there. It is a gradually increasing curve. So, this is how the reflectance curve of vegetation will look. So, what are the different factors that may affect the spectral reflectance curve of soil? We will see this in this slide. So, the major factors that affects the spectral reflectance curve of soil is the soil texture. So, soil texture generally means the size of particle in soil. Some soils may have like very tiny particles. Say for example, if you take like clay may be made up of lot of tiny soil particles that are closely packed together. On the other hand, if you take sand, like normally we might have observed in beaches, it may have slightly larger particles with a larger air gaps in between them. So, how the soil texture is, whether it is rough or smooth, whether it has like large number of or large grain particles, or whether it has small grain particles and so on, it will affect the reflectance. The major important property of the soil that will affect the reflectance is the moisture content, how much moisture is present within the soil. That is, whenever if you take about, or if you talk about like a volume of soil, let us say this is like a small vessel in which we filled soil to some extent. So, whatever be the soil is, there will always be a mix of soil particles plus some in between air gaps. So, whenever we pour water over this, or whenever it rains, then naturally the air gaps between the soil particles will be filled with water. So, essentially we will be able to measure how much is the amount of water present within a given amount of soil, be it like volume of water to the volume of soil, or mass of water to the mass of soil, etc. In general we will be able to measure how much water is present within the soil column. That amount of moisture content will increase or will normally decrease the reflectance. Then organic matter content. Organic matter content is substances that are rich in carbon. Say for example, this may be like a land surface, there may be like a tree standing, the leaves from the tree may fall down, decay, decompose and mix with the soil. There may be a small lot of tiny organisms present in the soil which may die and decompose. Other organic substances, most of the naturally occurring substances are organic in nature. So, all these organic substances may finally fall on the soil, mix with it or decompose. So, the amount of organic content present within a soil is going to affect its reflectance. The next property which may affect the soil reflectance is the amount of iron oxide, that is presence of iron materials or ferrous materials. Some soils we might have seen having like bright red in color, some soils may be like black in color. So, the red soils typically has high content in iron oxide or any other like iron content. So, those will affect the reflectance of soil. Then Soil salinity. Soil salinity is like saltiness of the soil, that is some examples we might have heard, that is when people use irrigation, like it is very normal to use groundwater for irrigation. We have also known that groundwater is present underneath the ground, which may, when we are like pulling it out, it may have lot of dissolved minerals within it, right, because like underground we have lot of minerals present in rocks, soils and everything. So, when water is there, some of the minerals present in the under the ground may get dissolved in the water. When we pump it, it may come to the land. We pour that water or we use that water for watering our crops. Similarly, farmers may add some fertilizers, some pesticides etc., which may again contain certain minerals. So, they will slowly start settling down on the soil. When all these things start settling down, then the soil salinity or the presence of salts in the soil will begin to increase. So, this soil salinity also may increase or decrease the reflectance. And finally, the surface roughness. Surface roughness is let us say like there is a smooth soil surface. Smooth soil surface means like a barren land without any human activity. Finally, everything will settle down, it may be looking like as like somewhat like smooth surface. On the other hand, a normal farmland where like at the beginning of cropping season what the farmer will do, the farmer will till the land surface or plough the land surface. When that happens, and if you look at the land will clearly have like a lot of small ridges and valleys because of the ploughing effect. So, which increases the surface roughness of the soil. So, all these factors, both the physical and chemical. Physical means soil particle size, surface roughness etc. Chemical means presence of soil organic content, presence of salt in the soil etc. All these things will contribute to the reflectance of the soil that we observe either in laboratory or from remote sensing measurements. So, now we will see the effect of each factor one by one. First, we will start with the soil particle size. In general, the reflectance of the soil will increase when the particle size decreases. So, this one example, here we have two curves, reflectance curves plotted, one for sand, another one for silt. Sand has larger particle sizes, larger particle size. Silt has much smaller particle size. So, when we plot like this, in general soils with finer or smaller particle size will have a higher reflectance than soils with larger particle size. This is when done in proper laboratory conditions, that is everything is like finely powdered to its natural state, observed under strict lab conditions. In reality, in ground, when we observe a sandy soil and a clayey soil, like clay soil is another one which has like very fine soil particles, much smaller, tiny smaller particles. So, if we observe these two, what will be our inference? Our normal observation is sand will look brighter to our eyes than this fine textured clay soil, but in lab we are getting the opposite thing. This is because in reality such fine textured soil such as clay or silt whatever may have the capacity to hold lot of water, or they may be like forming aggregates. Aggregates means like, say for example, if you take clay soil and if you pour water over it and leave for some time, they may come closer and form like small like tiny ball like structures. So, they may form like larger soil aggregates which will finally increase their net effective particle size. All these things may happen with soils having very fine particle size in nature, say example clay and silt. That is why in reality we may observe the contrary of what is observed in lab. So, in lab under controlled conditions, when everything is like finely powdered to its natural state, then fine textured soils will have higher reflectance than coarse grained soils, but in real life fine textured soils such as clay or silt etc. may club together or may come together to form larger aggregates due to presence of water or whatever be the nature, whatever be the reason. They will form larger aggregates which will reduce their overall reflectance. So, in reality fine texture like clayey soils and all may appear much darker to our eyes when compared to the sandy soils or soils with coarse grain texture. This we should always keep this in mind. A lab obtained curve may not be really valid in field, especially in case of this fine textured and coarse grained soils. We always have to keep this in mind. The next most important property that we are going to discuss is presence of soil moisture. So, as moisture content in the soil increases, the reflectance will decrease. Example is given here in this slide. So, this is reflectance of silt loam, it is a type of soil. This is like a fine textured soil. So, for such fine textured soil, so this is in the order of like increasing moisture content. So, the amount of moisture content is given here 0.8% is moisture, 4.7 moisture, 20.2% moisture and so on. So, as moisture content increases, in general the reflectance increases, the entire curve actually goes below. These curves they are not intersecting, they are just falling one below the other. So, overall in all the wavelengths the reflectance will go down as the moisture content increases. In addition to this, in earlier classes we have come across characteristic water absorption bands. So, either even in vegetation or even in atmosphere we have discussed that 1.4, 1.9 and 2.7 micrometers. These wavelengths are essentially water absorption bands. So, as the moisture content in the soil increases, at these particular wavelengths the reflectance will go down sharply. This is like much clearly seen in this 1.9 micrometer range. Around this 1.9 micrometer range, as the moisture content increases, the dip or the absorption feature becomes very deep with increasing moisture content. So, this figure or this water absorption will be prominently seen when the moisture content increases. In addition to this, for fine textured soil such as clay or silt, it may contain hydroxyl ions which may cause a characteristic absorption around 2.2 micrometers, that is given here. Around 2.2 micrometers we are having what is known as hydroxyl absorption band. So, that may also be there. As the moisture content changes, the hydroxyl absorption band also changes. So, here the hydroxyl absorption band is kind of doing the reverse of this water absorption bands. As the moisture content is increasing, the hydroxyl absorption band is becoming more narrow and narrow, and the big band is and the absorption band is becoming quite sharp as the moisture content decreases. So, these sort of features, but this hydroxyl absorption band will not be present in sandy soils. It is a characteristic of fine grained soils such as clay or silt. But here the major take home message from this particular slide is, as the moisture content increases, the overall reflectance of the soil goes down in almost the entire portion of electromagnetic spectrum, starting from visible to SWIR. In addition to this, increasing moisture content may lead to like a prominent absorption, water absorption bands. Those bands may become prominently visible or clearly visible in the wavelengths of 1.4, 1.9 and 2.7 micrometers. But as I said, when we discussed about vegetation, I said this characteristic water absorption bands 1.4, 1.9, 2.7 are also characteristic water vapor absorption bands that is present in the atmosphere. So, normally these bands we cannot use for understanding the amount of water present in earth surface features, because if we put any one band in say around like 1.4 or 1.9 micrometers, they will be absorbed in the atmosphere itself. We will not be getting any signal from the land, be it vegetation present or be it soil present. So, normally for water what we will do, we will use the EMR band slightly adjacent to this. We may use 1.5 to 1.6 or we may use 2.1 to 2.3, such bands we will use for monitoring vegetation. Same concept applies for soil also. Even for soil, using this exact bands around like 1.4 or 1.9, we may not be able to use it for understanding or characterizing the soil moisture content because of the presence of atmosphere and water vapor absorption in atmosphere. So, this slide again tells us the spectral reflectance of soil with increasing in moisture content. See, this is for sand. Sand is like a coarse grained soil, like it has larger particle size. For such larger particle size soil, the hydroxyl absorption band around this 2.2 micrometers is not there as I said. So, it is a characteristic of only of fine grained soils like clay. But what you can notice, whatever be the soil texture, be it coarse textured sand or fine textured clay, the overall reflectance decreases as the moisture content increases, plus the water absorption bands become very prominent. So, here also for clay also the same results hold good, the reflectance decreases, the water absorption bands become more prominent, and also hydroxyl bands we are able to observe only in fine textured soil such as clay or silt. The next property what we are going to discuss is soil organic content. As I said before, organic content comes because of the mixture of large amount of like living organisms or other organic manures that may be supplied to the soil. Say leaves may fall, organisms may die and decay, or the farmers may apply manure like cow dung may be applied to the soil. All these things will change the organic content present within the soil. In general, if you look at like organic matter, whatever be the source, after certain time of like decay and decomposition, when they become like when they mix properly with soil and when they become like crumbly nature, they will in general have a very dark color. So, that will be the effect of organic material in soil. So, when organic material thoroughly mixes with soil and when everything becomes like one single mass, the soil will become much darker in color. So, we may observe like dark brown soils, dark blackish soils whenever organic content increases. So, in general the presence of organic content in the soil will decrease its reflectance, that is given here in this slide. So, this is like pure sand, 100% sand, and we start beginning to add organic material to it. So, each curve represents different proportion of mixture of organic material and sand. So, as you can see, as the organic content increases, the reflectance decreases, and just see how the curve changes. Like we have seen that the curve for sand will look something like this, pure sand, it will be kind of increasing like this. But as the organic content increases, the reflectance in visible portion dramatically decreases and the curve becomes like almost inverted. Instead of being something like this, the curve becomes something like this. So, the curve is slightly having like a different shape. This is for pure soil, this is for soil mixed with organic content. So, here you can see the curve has become like tilted in a different direction. So, this is because of presence of organic material, and organic material, as I said, to our eyes it becomes or it appears really dark because it absorbs a large fraction of visible wavelength. So, that is why its reflectance is extremely low in the visible wavelength from 0.4 to 0.7 micrometers, and that is why when the organic content increases, the visible reflectance will go down drastically. The reflectance in all bands goes down or decreases, but its effect is much more clear in the visible portion. In visible portion it increases drastically, decreases drastically, which gives a characteristic dark color to the soil that is filled with organic material. So, some organic soils may be brown, some organic soils may be dark, it depends on the climate in which it is present, depending on the material with which it is mixed, everything. But in general, if the soil is pure in a region, it will have a higher reflectance when compared with the same soil after getting mixed with organic material. So, the next important property we are going to see is the presence of iron oxide. So, iron oxide, whenever it is present, it gives soil a characteristic red color. So, soil rich in iron material will have a characteristic red color. So, that is what we are going to see in this slide. Say this is like a loamy soil. Loam is like another type of soil which is a mix of like sand, silt and clay at different proportions. So, it will be having like a mixed texture. Okay, so this is like the general loam without any iron oxide, this curve. So, it is kind of like increasing naturally, but when iron oxide is added, a characteristic increase in the red band will come. So, around this 0.6 to 0.7 micrometers increase in red reflectance is observed, and there will be like a iron oxide absorption band in the NIR region around this 0.9 micrometers. So, this what gives a characteristic red color. This increase in red reflectance is what gives a characteristic red color to the soil that has abundance of iron oxide, plus the reflectance in NIR portion also goes down because of the presence of iron oxide absorption bands. So, this is like a general property of soil which contains iron oxide. So, next property what we are going to see is the soil salinity. So, in general soil salinity, like addition of salt to the soil will increase the soil reflectance. So, that is given here in this slide. So, increasing soil salinity, like it is increasing like this from a low soil salinity to like very high soil salinity. This in general increases the soil reflectance. So, maybe like soils that are like highly saline sometimes may appear like bright white in color. Normally like people use satellite images to observe the saline nature of soils over certain regions. It is one of the important applications of remote sensing. So, soils with very high salt content will generally have very bright reflectance. It may appear even white in remote sensing images. When we combine certain bands together and see them, it may appear white because of the increased reflectance due to increase in soil salt content. So, the presence of salt in the soil will in general increase the soil reflectance. Then one more property that we have discussed is soil roughness, I said. So, soil roughness is like whether a soil surface is kind of really smooth without any tillage or something, or when it is like plowed, or when it is being disturbed by some other thing, like some animals may come, may dig the soil with their legs, which will increase the surface roughness. When such thing happens, normally when the surface roughness of the soil changes, what will happen is soil particles may kind of come together and form like large clumps. Say farmers may plow the land, may supply some moisture to it, all these things may happen, which will make the soil to form like clusters, like different clusters can form together. When such clusters forms due to the change in surface roughness, then the reflectance may go down. That is what we have seen, like large grained soil may have like a lower reflectance. So, the effect of soil roughness, that is when the soil roughness changes, then effectively the reflectance also will change, but it is not like a uniform property, especially the soil roughness thing is not a uniform property. Several other factors such as moisture, organic content, everything will influence it, but roughness is also one of the important thing which we should remember when we observe the soil reflectance. So, this brings us to the end of spectral reflectance of soil. Actually, spectral reflectance nature of soil is quite a very simple topic, because as I said, even the reflectance curve do not have like a large number of characteristic dips and peaks which needs detailed explanation. Whatever be the factor, whether it is moisture or salinity or soil particle size, whatever be the factor, most likely it increases the soil reflectance overall in all the wavelengths, and the presence of like the absorption bands are very minimal in the soil reflectance curve. That is why it is normally very easy to understand the different properties that affects the spectral reflectance nature of soil. But one thing we should always remember is, I clearly told you that a soil reflectance curve obtained in laboratory may behave completely differently when we compare this with a reflectance curve obtained from field measurements, because in field lot more factors influence soil's reflectance. So, remote sensing of soils, though it is being carried out very frequently, we always have to observe caution, that is, we should not simply match the curve obtained from lab with what is being obtained in field. We should take into account all these factors. Okay, in reality what was the soil particle size, what was the soil particle size that was used in lab, that will cause a change. What is the amount of moisture content in the field when compared to the moisture content used in lab, that is going to give us a change. So, all these factors we have to keep in mind when we match the spectral reflectance curve obtained in laboratory with the spectral reflectance curve obtained from field measurements. So, remote sensing of soils especially is not like a straightforward task. In addition to all these, presence of vegetation or some other structure over the soil may prevent us from observing the soil itself. When a tree is present over a soil, and if our goal is to get information about the soil itself, we may not be able to get it. We may be getting the signal only from the vegetation, which is we do not want at this stage. So, lot of other features present over the soil may contaminate the signal or may cause its own signal rather than giving us the spectral reflectance of soil. So, we should always have all these points in the mind when we do remote sensing of soils. With this we end this lecture and also the topic of spectral reflectance of soil. Thank you very much.